Welcome everybody to episode 9 of Games with Go. Today we're going to be doing some cool graphic stuff with noise functions. and some other big news is over the last month, enough people have watched that the channel has qualified for being a Twitch affiliate, which means you can subscribe for $5 a month and you can watch without having to see any ads if you want to. And also, if you have a Amazon Prime account, you can use that to subscribe to one Twitch channel per month for free. So if you don't like the ads, feel free to go for it. Okay, so today we're going to be talking about noise. So what are noise functions? So the simplest type of noise, if we were to represent it on like a line here where the x-axis is your input and the y-axis is your output. The simplest form of noise would just be to pick random numbers at each step. So you would just get a complete mess like that. And that might be fine for some things, but a lot of times when you want to generate noise, you want something that has a more natural feel. The way that like a coastline might be random but has some order to it, or the mountain range, like its profile is random but has some order to it. And to get those kinds of effects, we use something called coherent noise. And so coherent noise has two important properties. The first one is that if an input is close to another one, then the output will also be close. And the other property is if the inputs are far away from each other, then the outputs will be random and unpredictable. So our previous example with just random points would fail the first requirement for coherent noise because inputs that are close to each other could be very far apart. And if you imagine using something like a sine wave, like a very regular sine wave, that would fail the second requirement because while inputs that are close to each other are always close, you get a nice continuous curve. Inputs that are far apart are very predictable, right? You always get the same thing if you keep going at regular intervals. So how do we make coherent noise? So there are at least two broad categories. One is called value noise. And that's one of the simpler types. It's a little easier to compute, but doesn't look as good. So if we were to represent one-dimensional value noise on our number line, the way you would make it is you pick some regular intervals along your number line on the x-axis. And at each point you come up with a random number. All right, so this might be 1, this might be -1, this might also be -1, 0, maybe 2, back to 1, something like that. And then to fill in the spaces between your regular intervals, you do a linear interpolation. So you might remember we talked about linear interpolation a little bit when making Pong. This comes up again here. So to linear interpolate between 2 points, if you were to go halfway between the points, you just basically draw a line at the halfway point, draw your dot. So if we did the linear interpolation all the way, we just get lines that connect the dots. Very simple concept, right? So now we might end up with noise that looks a little better. So it's coherent because inputs that are close to each other are now producing outputs that are also close to each other. It's a continuous curve. There's no discontinuities. And outputs that are far apart are random and unpredictable. Could be anywhere. But it doesn't look so much like you might expect a natural feature to look with these sharp points and stuff. And when you extend this into 2 dimensions, you get some similar artifacts. And you also noticed here, if 2 of the random values happen to be the same, you get like a flat spot. So this has some undesirable properties, but it does work fine in certain use cases. And there are lots of games that use value noise as the basis for making geometry or textures in their games. It can look fine a lot of times. So the other broad category that can look a little bit nicer, but takes a little more computation, is gradient noise. This should be a D. Okay, so gradient noise, the other type of coherent noise, or another type of coherent noise. Similar idea, where you have some random things you pick at regular intervals. But in the one-dimensional case, rather than picking a random point at each of these values, you pick a random slope. So you might imagine we have a slope like that there, maybe like that, maybe a really steep one, maybe a shallow one. And then instead of linear interpolation from one point to the next, you linear interpolate the slopes. So what that gets you is a nice smooth curve from one slope to the next. And so you end up with something that looks more like smooth lines like that. All right, so that's what gradient noise would look like if you represented one-dimensional gradient noise on a line. And there's two common types of gradient noise. There is Perlin noise, which is sort of the original and most famous. And this name is often used as an umbrella term for all of these types of noise. Like you'll see games that use value noise and people call it Perlin noise. They all kind of look the same once you do certain effects with them. And there's also Simplex noise. Same guy, Ken Perlin, invented both of these. And Simplex noise just looks a little nicer. And there's also Open Simplex. And there's probably many other variants that people have come up with, all following the same basic idea. Okay, so what do we do with this stuff? What's the point? So the idea is to be able to do procedural generation. And games and even movies and art programs use this for creating various types of natural effects. And that could include textures that look like clouds. It could include geometry that looks like hills or mountains. There's just all kinds of natural effects that this noise can kind of produce with different input parameters. And one of the techniques we use with noise is called fractal noise, or fractal Brownian motion is the fancy name for it. It sounds really complicated, but it's actually a really simple idea. So you might have, say you had some one-dimensional noise and you produced some sort of nice curve like this. Why did that turn a different color? There we go. I made it transparent somehow. All right, so say we had a nice curve. Right, and you might imagine that looks a little bit like the profile of a hillside or something. But of course, a real hillside would have more detail on it, right? There might be little undulations within the hill. There'll be little rocks and pebbles and stuff on top of those undulations. So what if you wanted to get an effect more like that? Well, what you can do is you can change the frequency of the noise you're producing. So you might end up with like this exact same curve on a smaller scale, right? And it's got additional stuff that happens at the end. And you can do it again at even a smaller frequency, or higher frequency. And what you can do is end up layering these things together, kind of averaging them up or summing them up, and you end up with a net result that looks like a very natural, coastline type shape if you want, or hillsides if you're doing like a one-dimensional thing like this. And so that's the basic idea of what we're going to do. So let's get started with some actual code. And if anyone has questions, fire away and chat at any time. I'll be checking in on it. So we're going to start a new folder here in VS Code. We'll call it Simplex Noise. And then we're going to open a new file, simplexnoise.go. And we're going to grab our code from the SDL2 episode, the one where we just did the setup. So this just has the code to like set up an environment where we can draw to the screen. And if people are following in another language, at this point you'll just want to have some kind of setup where you can draw pixels to the screen. If you can do that, you'll be able to follow along with the noise stuff we're going to add to it. Okay, so this should all be good for now. Okay, so next step is we need a simplex noise function. The simplex noise function's pretty big and messy, and what people usually do is there's various reference implementations out there. One of these is by this guy, Stefan Gustafsson, I think his name is. He has various noise functions implemented in C for 1, 2, 3, and 4 dimensions. So what you can do is go to something like this, this implementation is in C, and you can port it to Go yourself. It's not too hard. You just go through line by line, convert things to Go syntax. It's pretty straightforward. But that would also be pretty boring to watch on stream, so I've done this ahead of time for you. And if you guys want to follow along, you can go to this link on Gist. You can hit raw, and you can just copy and paste this into your file. And I'm just going to throw it down here at the bottom. Okay, so what we have here is we have this permutation table. This is just basically 256, 0 through 255 arranged in random order in an array. And the simplex function makes use of this. And we have a gradient function, and we have a simplex noise 2D function. So for now, don't worry too much about the details of how this implementation works. We're going to be talking about kind of higher level things today. If you do want to get deep into exactly what is going on with simplex noise in detail, I recommend this website. This PDF is a good place to start. Also written by Stefan Gustafsson, and I'll put a link to that in chat. So like if you wanted to do your own implementation from scratch or do a derivative implementation, this would be the kind of thing, like read this and understand it, and you can start playing around with it. Okay, so at this point we have a simplex noise function, which we can give x and y values as floating point values, and we get back a noise value as a floating point as a result. All right, and that's what makes it two-dimensional, is it takes in two inputs, x and a y. Okay, so let's head to, let's make a new function which will take in, or which will basically draw us a whole screen full of noise, like fill our 800 by 600 screen full of noise. So we'll call that make noise. And we will first want to, let's just start by spitting out some noise and see what it looks like. So we will say for y is equal to 0 to min height y plus plus, for x equals 0 width x plus plus. So we're going to go through all the x, y values on the screen, and we're going to call our noise with that x and y, and just see what we get. we're just going to print line these to console just to kind of see what the values look like real quick and make sure it's working. Oh, these need to be floats. Let's see, what are we unhappy about here? There we go. So let's go into our Simplex noise, go run simplex noise.go. Oh, okay. That makes sense because we were this is our old test code. So let's delete our old test code that fills the screen with pixels. And let's just call make noise here one time. Don't need to do it over and over. All right, so we see we're getting lots of floating point values down at the bottom. So the thing about these noise functions is they output noise values in some range, right? In this case, it looks like it's from negative something small to positive something small. Now you can scale these just by multiplying and then adding to be any range you want. So for us, since our color array uses bytes, between 0 and 255, we'll want to scale this to between 0 and 255. So we can make each one of these values represent some color. But the thing is, once we start adding our noises up together to do fractal noise, is that this range will change depending on the parameters you provide. So for us to be able to test and play around with this, what we want to do is have a function that can rescale whatever value ranges we happen to get every time we run this. So what we're going to do is we're going to make a rescale function. And what that's going to do is take the values we get in our noise and rescale all of them to be between 0 and 255 for us. So one thing we're going to want to do is collect our noise into an array from the get-go. So we'll make a noise array, which will be an array of float 32s, and it will be same size as the width times height of our window. So we can store a floating point value for every bit of noise we've got. And then we will set that in here. That's the easiest way to do this. So noise of I equals S noise 2. So now we're filling up the array with noise, and then we'll increment I each time. So now we want to rescale this array. So in order to know how to rescale the array, we also need to know the minimum and maximum noise values we've gotten so far. So rather than having to iterate through the array 3 times, we'll go ahead and keep track of the min and max value as we go. So what we can do is say minimum equals something very large. We'll make sure this is float 32. We'll say max is equal to something very small. And then if noise is less than the minimum, then the minimum equals noise. Else if noise is greater than the maximum, maximum equals noise of I. And then so our rescale will want the minimum and maximum values that we got as float 32s. And it's also going to want the yeah, so let's go ahead and pass in our pixels. So we have a pixels array that represents the screen that we're going to draw to. Let's go ahead and set that in here too. So we're going to rescale, or maybe say rescale and draw. We're just going to go ahead and draw whatever values we get straight to the screen. So yeah, so we'll take our pixels, which is a byte array, and we also need our noise. So the noise is going to be the float 32 array. Okay, so we're going to take our noise, the minimum and maximum values we found, and our screen buffer to draw things into it. So the scaling factor we're going to use, right? Our values might range between anything, say 0 to 1,000, and we want to squeeze that to 255. Or if the values range from 0 to 10, we want to expand that to 0 to 255. So we're going to take the scale is equal to 255 divided by the difference between max and min, right? This is the range of the noise values we got, and we want to scale that to 255. And then we want to have an offset to push that range to start at 0 and count up. So offset is equal to the minimum times the scale. And I think this is just mad because we're not using it yet. Yeah. So then we're going to go through each noise value. Okay, this is for each index in the range of the noise array. We're going to multiply the noise times the scale and then subtract the offset. All right, and then now that we have a scaled noise value, we can come up with a byte value. So we'll say our byte B is equal to basically int of f of I. So we're just going to make this floating point value an integer. And then we can set our pixels let's see, P, yeah. So our pixels go 4 at a time because we have RGB and alpha. So we'll just set them all. +1, +2. So RG and B we're all going to set equal to this byte value. So it's just going to be black and white to start with. So let's see, what's the problem here? Oh, this is calling this noise, not F. Undefined noise again. That should be byte. Okay. So now we have our function that will rescale the noise and turn it into bytes and set our pixel array with that byte at each step. So now make noise also needs the pixels. Pixels byte. So at the end of this for loop, we will have our noise array, and then we can call rescale and draw with our noise, and our min, and our max, and our pixels. This will need the pixels. So let's give this a try. All right, we've got some noise, but this does not actually look like it's coherent noise right now. It just looks like a bunch of random dots. And the reason for that is that the frequency is kind of like zoomed way out on the noise. So let's play with the frequency. Let's try some different values here. All right, now we're getting something more like what we expect. This is sort of what simplex noise looks like. And you might think, well, that's not really very cool, is it? It's just kind of a blurry black and white image. It kind of hurts your eyes to look at it. But it turns out there's a lot of potential here once we start doing things like adding fractal noise on top of it and adding color. So let's get started with that, because it turns out that the fractal noise function is actually really, really simple. Much simpler than simplex noise itself. So, fractal noise. What does that mean? What is it? So that is the idea we talked about before, where we take the noise at one frequency and combine it with the same noise at another frequency, and so on. So let's start typing up the function. We will call this FBM for fractal Brownian motion, the scary sounding name that is actually pretty simple. So this is going to take in our x and y, just like the noise function did. And it's going to take in a bunch of parameters. Frequency, lacunarity, which is a word that I don't know where it comes from, but it refers to the rate at which we will be changing the frequency through each iteration. Gain, which is the rate at which we will be changing the amplitude of the noise through each iteration. And then octaves, which is how many iterations we're going to do. Right? So in our drawing here, this would be 3 octaves with the frequency and gain changing each time. So those are the input parameters. There's a bunch of them. And you can tune them all sorts of different ways to get all sorts of different effects. So the implementation looks like this. We're going to have a sum. This is a float 32, and it'll start at 0. We're going to have an amplitude, which starts at 1. And then we're going to iterate through each of our octaves. So for I is equal to 0, I is less than octaves, I plus plus. And we're going to say sum is equal to the sum plus simplex noise of x times our frequency, y times the frequency, times the amplitude. Right, so you remember before when we changed the frequency, it's like we zoomed in to our values. When we divided, we zoomed in, we multiply, zoom out. And then amplitude can just make everything, the resulting numbers, bigger or smaller. And then the frequency is going to change each iteration as well by multiplying it by the lacunarity. And the amplitude will change each iteration by multiplying it times the gain. This is going to need to be, wait, why is this not happy? Oh, S noise 2. Okay. Then when we're all done, we just return the sum. So it's super short, but it has really, really big effects. So it is really fun to play with. So all we change down here is instead of calling S noise, we call FBM. Now we also have to provide all these extra parameters. I think did we call it FBM2? Yeah. Right, we've got frequency, which I don't know. We'll start with 0.01. Lacunarity, start with 2. Gain, 2. Octaves, 3. Now, if you haven't played with noise a lot, you'll have no idea what to set these values to. And if you set them to values that are too big or too small, you kind of get bizarre results that don't look very nice. I think this will look nice. I have some experience with this, but I don't remember for sure. We no longer need to divide by 100 because that's going to be built into the frequency. So let's see what we get. All right, that is not all that interesting. Looks kind of like before. So let's try some different values here. So let's try maybe 0.5 and 1. Still keep the octaves at 3. Let's see what we get. Still not very interesting. So what you're starting to see here is one of the problems when you need to play with a function like this where you have lots of input parameters and you're not sure what the best one should be, this iteration cycle of going through and changing the code, compiling and running it, and seeing what you get it's kind of slow and laborious, and it's hard to get a really good idea of what's going on because you have these delays between each iteration. And this kind of problem can come up in game programming all the time, or programming of any type all the time. And what you want to do when this happens is set up a way to change these parameters at runtime so that you can really quickly explore the problem space and understand it better and get results quicker. So let's do that. Let's make some kind of interface where we can change these at runtime. Now we haven't done any kind of like GUI stuff yet, so we don't have buttons or stuff we can use to do that. But we can make a really simple text-based or keyboard-based interface. So let's do that real quick. So what we're going to do is we're going to keep track of our key state, just like we did in Pong. So we'll go here. First of all, we're going to move stuff into our game loop. And we need to keep track of the keyboard state. So we're going to make our key state array by calling sdl.getKeyboardState. And then we're going to create a little multiplier. I'm going to set it equal to 1. We'll see what that's for in just a second. What we want to be able to do is change all of the parameters to our fractal function. Mars is asking on chat, if our lacunarity is less than or equal to 1, wouldn't your frequency decrease with every iteration and blur out any visible effects into the gradient like the pattern you're seeing? And yes, that is probably the problem, is we should probably have a lacunarity that is higher. But we'll be able to see that really quickly when we set up this little interface where we can play with things at runtime. And we'll get to see all sorts of neat effects by playing with that. Okay, so multiplier is going to be 1. And then what we're going to do is if someone holds down the shift key, that will decrease a parameter. And if they don't hold down the shift key, we'll increase the parameter. So we're going to look for scan code L shift or right shift. Okay, so if either of those are being pressed, we're going to set mult equal to -1. Then we're going to pick a key for each parameter that we're going to change. So for instance, for octaves, we might pick the O key. So if that's not equal to 0, we'll say octaves equals octaves plus 1 times the multiplier. So if holding shift down, it's going to subtract 1. If they're not, it's going to add 1. SDL.scan code. And we'll do F for frequency. And we will just add a little bit to frequency, or subtract if shift is being held down. And then for gain, we'll do G. So a lot of times for programmers, they can hesitate to do this kind of thing because it takes a little bit of upfront work, and they think maybe if they just try a few more iterations of recode and recompile, they'll get what they want. But this usually pays off in the long run. This is something that you'll have forever to play with noise, for instance, in this case, and really explore different effects. In the long run, it saves time, even though it wastes time up front. Okay, so the lacunarity. And so we're going to want to set some initial values for these things. So we'll do frequency It's equal to float 32 of 0.01. We'll do gain float 32.2. Lacunarity float 32 of 3. And octaves of 3. And we'll have our make noise take in all these same values too. So frequency, lacunarity, gain, all float 32, octaves int. Frequency, lacunarity, gain, octaves. All right, so we'll get our initial render there, and then we'll want to call this anytime the value is changed. Redraw those pixels. Then up here, lacunarity, gain, octaves. That will push it all the way up the stack to FBM. All right, are we good there? Let's give it a try. Okay, so now we're seeing our first effect that's a little bit more interesting. This kind of looks a little bit like clouds or something. So we can change our frequency. We see how we start, kind of looks like we zoom out. If we hold down shift, it's like we're zooming in. We can change our gain. See how we get like kind of different details as we change the gain. We can change the octaves. That's 1 octave, so this looks like simplex noise, which is what it is. We start getting different kinds of details. So you can really play with all the different parameters, different combinations, to get lots of different effects going on. But it still maybe doesn't look super interesting, right? Like, we're just getting some kind of gray clouds and stuff. What good is that? Someone asked if we can print out some of the values so we can see what the values are. We can. Let's see. The best place to do that would be in the rescale function. Or do you want to see the values before or after they've been scaled? Because they're all going to be 0 to 255 after they're scaled. Like we could print line here. Don't know how long it'll take to print them all, so it might be kind of crazy. Yeah, it's going to be real slow. But you could do something where you print out like a selection. Oh, I see. Yes, that is a good idea. So what we should do is in our make noise, let's print out all the parameters we're using. So as we're moving things around, we'll see what it is. So we'll do frequency, lacunarity, gain, octaves. Let me pull out that. Let's get rid of that. Okay, so yeah, now as we play with things, we can see what the values are. And that is an excellent idea. That would be very useful. And if you do something weird like that, you can see why. We've gone negative on the octaves, so nothing's happening at all. All right, cool. All right, that lets us play around with stuff real fast. Okay, the final step to make things start looking really cool is to provide color gradients to replace the black and white thing we're doing. So how do we do that? The first step is we're going to want the ability to do linear interpolation between colors. And there are fancy ways to do that, and there are simple ways to do that. And I'm going to do the simple way, which if you're like a serious artist, you'd probably cringe at it. But it looks fine for most use cases. So let's just do that for now. So If you remember linear interpolation from the Pong episode, the idea is you take two values and a percentage that you want to interpolate between them and come up with something that is in between them according to that percentage. And to do that, we'll need another helper function to lerp between byte values. So we'll do b1 byte, b2 byte, and percentage, and that will return a byte, which is a linear interpolation. So this is pretty simple. We'll take the b1 plus the percentage times the range of b2 minus b1. Let's see what's the problem here. Just make this byte. Float 32% times float 32 b2 minus b1. There we go. Okay, so this will give us linear interpolation between two bytes. And then for colors, we just do a linear interpolation of each component, the red, the green, and the blue, to make a new color. Which again, there are fancier ways to do that are more precise, but this works pretty well. So we're going to do the red, the green, and the blue. And this returns a color. And what are we unhappy about? Lerp, not lepper. Cool, now we've got a color lerp function. And then we'll do a function to get a gradient. It'll take two colors and return an array of colors. So we're going to make a new array, 256 big. This could be any value. You could have a much bigger gradient than you want. This will be like old 256 color gradient days. Then we'll iterate over that array, get the current percentage, VR down the array, and we will lerp between color 1 and color 2 all the way down. So if we give this a red and a blue, we'll get an array that goes gradually from red to purple to blue at the end. That is the idea. Range result. Misspelled float. Then we return the results. Okay, now what we want to do is make our rescaling function take in a gradient. So this will also take in a gradient, which is a color array, and use it to color the array. So the way we'll do that, once we've scaled our noise, we'll say that the color is equal to the gradient. We're going to do another function here, clamp. So clamp is another handy function in graphics. You take a min and a max and some value. And you just say if v is less than the minimum, v equals the minimum. If v is greater than the maximum, v equals the maximum. Then we return v. This just ensures that a value is between the range you want. What are we unhappy about? Oh, this Go wants this here. Okay, so we're going to say that we're going to use that to make sure that these values are in the range we want. So we're going to say C is equal to gradient clamp, because if we index the array out of bounds, the program will blow up. We don't want that. This will be our color, our pixel index. This may be more efficient if the compiler doesn't figure it out. Will be c.r, c.g, c.b. So we're getting our color by taking the noise value as an index into our color array and then setting our pixels to that color. All right, so instead of black and white, we can make it from red to blue, red to green, whatever we want. So we need to give it a gradient. So for now, where's our make noise? Let's say that gradient equals get gradient. Color, we'll give it red. And we'll give it blue. We'll pass this gradient to there. All right, so now we've got kind of a cool effect. And again, we can play with the frequency and octaves and gain and so on to get different things. Let's try zooming in here. I'm just typing wildly to see what we get. So that's pretty cool. And you can imagine if we did like a kind of yellow color. Let's see. What's a good RGB for yellow? So 255, 242. That is incorrect. Oh, red and green. So here you see how you can have kind of a cool fire or lava effect, right, that you can start to work with here. But let's take this one step further. Let's make a dual gradient. And you could extend this into any number of colors. You could make a generalized one, but we'll just do 2 for now. So we're going to get 4 colors this time. Get back the same color array. And start with this as our function. And what we're going to do is we'll say if the percent is less than halfway, then we'll lerp between C1 and C2. We'll have to multiply the percentage times 2 because we're restricting it to 0.5. So this will give us all the colors between C1 and C2. But for the other half of the percentage, we will color alert between C3 and C4. Multiply that by 1.5 and offset by 0.5. Again, this just keeps the actual lerping for this in the 0 to 1 range, even though we're going from 0.5 to 1 for this half. So that's just a quick way to, instead of lerping between one color and another, we go from color 1 to color 2, and then we suddenly switch to color 3 and then 4. So I've got some colors picked out ahead of time for this. Where's our make noise? So now let's do get dual gradient. And I picked out some colors ahead of time. We're going to go from kind of a blue color up to a light blue color, and then we're going to switch and go from a kind of green to a white. So let's see what that looks like. Okay, so yeah, someone in chat said surface of the sun texture, which is exactly right for that previous one. So now what you might be starting to see is this looks kind of like continents or islands or coastlines in an ocean. And so you can zoom in on here and get bigger islands. And we can also see if we drop the octaves down to 1, you'll see what I was talking about before. Here we have these smooth, high-level shapes, so a kind of islandish, but not really. They just look like blobs. But as we add an octave in the fractal noise, we get details on top of our old smoother details. And if we keep adding more octaves, we get more and more fine details added. You can see we get a little indentation there in the continent. And so this is how a lot of the games you see that have like procedurally generated planets or procedurally generated terrain like Minecraft, this is the kind of thing they're doing. They're using these types of gradient noise or value noise, and then using fractal noise to layer the detail on top of it to get kind of realistic coastline type things. Now you can take the same kind of data and turn it into a height map. So instead of using the noise values to represent colors, you can represent heights for geometry. So you can imagine a big grid, and at each point along the grid, you move the vertex up or down based on the value of the noise, and that can give you an actual 3D terrain that looks like natural mountains and valleys and so on, which is exactly the way games like Minecraft work. That's how they build the voxel geometry, is using noise functions like this. And of course, they do lots of other things on top of it, like run rivers on it, through it and stuff. But it all starts with this kind of noise stuff. Yeah, it's exactly what Minecraft does during their world generation. And the reason games like Minecraft or Elite Dangerous use techniques like this, the area of a Minecraft world, a single Minecraft world, is 8 times larger than the surface of the Earth. So there is no amount of artists you could hire that even in a million years could build that much terrain. So you have to use some sort of automated system. And Minecraft actually builds it as you walk along. If you kept walking along long enough in a Minecraft world, it would fill up your hard drive with noise values, basically. Okay, so let's see. Was there anything else I wanted to touch on today? Oh, yeah, we've got a few more minutes. So let's do another type of noise generation, one called turbulence. This is just to illustrate that there's lots of different things you can do with something like simplex noise or value noise or Perlin noise as a basis. And all the techniques we're doing here, this fractal thing works with value noise and Perlin noise just as well. It might look a little less good. I honestly can't really tell the difference, but some people can. I'm sure it depends what parameters you use as input. All right, so we're going to do another technique called turbulence. We might go a little over an hour here, and that's okay. You can watch later if you have to go to sleep or something. So this takes in all the same types of parameters as does fractal noise. And we have a sum just like before. And an amplitude just like before. And we iterate through our octaves, just like before. Then we'll get our noise value, x times frequency, y times frequency. And we say if f is less than 0, this is basically just getting an absolute value. The built-in absolute value function in Go uses 64 bits, so this is just avoiding doing that conversion. So we get the absolute value of our noise, so any negative values become positive values. And why is this unhappy? And then we add f to the sum. So then all we need to do is go to our make noise and just swap out turbulence for FBM. All right, now you kind of see like squiggly lines with little tributaries and stuff. And again, we can play with our values a little bit. Change our gain, change our lacunarity, put the gain back down. So this, you know, you can imagine maybe making like river type effects like this. If we go back to our, let's see, get dual gradient. If we went back here to our kind of fire colors, you kind of get pretty cool star looking effects. What did we say it was yellowish, 255, 242. So here again, you can see pretty cool effects. And some other things you can do with these types of noise is you can use three-dimensional noise and take a two-dimensional slice of it, just take an X and Y slice, and then move through the Z value, and you'll get really cool animations where these things will kind of like look like they're bubbling and like, you know, moving in a sensible way, because it's like everything's slowly like moving around as you move through the third dimension. So that can give you some really cool animations. You can also use 3 dimensions to be able to, like, if you want to texture. Sorry, my headphones shut themselves off after 30 minutes. If you want to put a texture on a sphere, you can generate 3D noise so that the noise will cover a sphere without being distorted. So you just use the actual 3D values in the 3D noise along the surface of the sphere. That's how people tend to make planets and stars with noise. So they use 3D noise, map it to a square texture, which gives you the distortion you need to then wrap it around the geometry. All right, so that is it for tonight. What we're going to do next episode is we're going to do some things to speed up noise generation. I'm on a very fast computer, but you might notice this doesn't happen quite instantly. If we made this, 1080p or 4K, it would get way, way slower. So we're going to learn about how to do parallelism in Go, so we can use all the cores on our machines to draw the noise faster. And we're also going to learn how to turn this into a package so that we can use this as a library in other things we do in the future. So we'll learn about the concept of making a library in general, as well as how do you do packages in Go specifically. All right, any questions before we go? Otherwise, I will see everyone on Tuesday. All right, thanks everyone for tuning in. And remember, we are now a Twitch affiliate, so if you want to watch without commercials or just want to contribute to this series, you can subscribe. And if you're an Amazon Prime member, you can use that to subscribe to one Twitch channel free per month. All right, thank you everybody. Good night.